is a quick overview of alcohols. They have the general formula in CnH2n plus 1 OH. So they contain the OH functional group, an O bonded to an H, and the O is also bonded to the carbon of the chain of the alcohol. When naming the alcohols that is bigger than ethanol, show the position of the OH group by inserting a number. For example, butane 2-ol, so the number where the alcohol group is in carbon number 2, this case counting from the right hand side. Alcohols are classified as primary, secondary and tertiary, just like haloalkanes were. In butane 2-ol, for example, we find that's a secondary alcohol because the carbon attached to the OH group has 2 other carbons attached to it. Secondary and tertiary alcohols are more reactive when it comes to substitution. So how do you make an alcohol? Well, the most common alcohol is ethanol. It's got 2 carbons in it. It's often made by fermentation, where yeast convert the sugars in a non-oxygen containing environment into ethanol and carbon dioxide. You can also prepare them in the lab or in industry. One way is by addition, so reacting with steam at a high temperature and a high pressure, and using a phosphoric acid catalyst. Now we express that with this here with the H2O/H+, symbolizing the acid catalyst there. And we've covered this in addition, so I won't go into it. This is the major product. Or you can prepare it by reacting the alkene with concentrated sulfuric acid and then followed by heating with water. Also has the same effect, so it's an addition reaction where water is added. And we can use the same symbol for those 2 reactions. So you've got your butane 1-ene here forming butane 2-ol, the major product. Visualizing this process, we've done this through addition as well, but there's bonds break, new bonds form, and there's our alcohol. That's the major product, where the H and the OH are attached to either atom of the CC double bond. You can also make a diol, which is like 2 alcohol groups, and we've covered this in addition as well, using potassium permanganate. Now I showed the /OH there, OH minus, showing that OH minus ions are important in this process, but this will happen just in neutral water as well. So how do alcohols react? Well, I've divided into 4 different categories here: combustion, which is burning; substitution, which is 1 atom on, 1 atom on, 1 atom off, 1 atom on; elimination, which is the formation of a CC double bond from a saturated compound; and oxidation, which is a new reaction type. Alcohols are good fuels. They're used often in racing cars. Not at the moment though, in lockdown. But so what happens is just burning with oxygen, producing carbon dioxide and water. Substitution reactions are important for us to look at, and there's some new reagents involved here. The substitution is a substitution of the OH group of the alcohol with a chlorine atom, and you can do this with very reactive reagents: phosphorus trichloride, phosphorus pentachloride, or thionyl chloride. This is a new one here. Those 3 can be used to do the same job. Basically, they add a chlorine to the molecule, take off a OH. Concentrated hydrochloric can be used as well, hydrochloric acid, but it can only be used with tertiary alcohols. So here's some examples. This first one is phosphorus pentachloride doing the job, so converting propane 1-ol into 2-chloropropane. And this is thionyl chloride doing it with a different alcohol. This is butane 2-ol. Notice how you put brackets around the OH when it's inside the condensed structural formula. And then you have the chlorine. You don't need to put brackets around chlorine because it's just 1 element, whereas OH is 2 elements. And this is the tertiary alcohol reacting with concentrated hydrochloric to produce a haloalkane as well. Now another reaction type is elimination. As I said, it converts a single bond into a double bond between carbons. So concentrated sulfuric acid can be used to convert an alcohol into an alkene. So what is eliminated is a water molecule. So elimination takes a small molecule off the molecule to produce the double bond. So here we have butane 1-ol being converted by concentrated sulfuric acid into but-1-ene. Now there's only one possible product here because the OH comes off the N carbon, so the hydrogen to make the water must come off the adjacent carbon, the next carbon in the chain. However, if the OH group is inside the molecule, like this one, this is a secondary alcohol, butane 2-ol, you get two products, the major and a minor. And the rule for this is that the pore will get poorer. In other words, the carbon next to the carbon with the OH with the least hydrogens will lose one. What about oxidation? Well, primary and secondary alcohols can be oxidized by strong oxidants such as acidified potassium dichromate, which we write as like this, or acidified potassium permanganate. Only primary alcohols will form carboxylic acids. So this is a new homologous series we're talking about here. So secondary alcohols will produce something called a ketone, but we don't look at them this year. And also in these reactions on the screen here, they actually go through an intermediate product, which is an aldehyde. But again, we won't look at it this year. We'll just consider them going from the alcohol into the carboxylic acid. So a couple of examples here. Ethanol being oxidized by the dichromate ion mixed with acid, H+, to produce ethanoic acid, which is common in vinegar. And methanol can be converted by either of these oxidants, and it will produce the carboxylic acid, methanoic acid. Now, looking at the physical properties briefly, alcohols are polar compounds because they have polar molecules. In other words, their molecules have a positive and a negative end on them. So I've drawn an alcohol here, methanol. You'd normally write it CH3OH, but I've just drawn it as a molecule with the O as the negative part, and then the rest of it is sort of positive. And so you can get some interesting effects. It's a bit like water when you have the little diagram there showing someone holding up a charged comb, a statically charged comb, up to a water stream. Will bend it, and you can have the same effect with alcohols. So what sort of properties does this polar molecule give the alcohols? Well, it gives them a relatively high melting and boiling point. It enables them to dissolve into quite other polar substances such as water, and they can also dissolve salts like water can as well. So when we're dissolving a salt in alcohol, for instance potassium hydroxide is shown there, dissolving, you'll represent it like this, KOH brackets ALC bracket. So that just means dissolved in alcohol. Now I've done this one because we use that for elimination, don't we? That's elimination of haloalkanes. So alcohols are polar. So you've got your positive and your negative side. So that little Greek symbol there just means slightly negative and slightly positive. So this little bond here that's what it causes the molecule to have a positive end and a negative end. And it affects their intermolecular forces. And the intermolecular forces, that just means the forces between one molecule in the substance and the next molecule in the subject. So in other words, what keeps it together as a liquid or a solid. So methanol, for instance, has a comparatively high boiling point because it has strong intermolecular forces. So the molecules are attracted to each other and move towards each other with a sort of attraction. So that has to be broken if you're going to boil it. So you've got to put a lot of energy, a bit more energy in than you would other small molecules to actually separate it and convert it into a gas from a liquid. It also helps them to dissolve in water, so they're quite attracted to water molecules, and water molecules are attracted to them because both of them are polar. So that helps them readily dissolve in water.